LEXPDIS. Enjoy your webinar. Thanks so much.
Thank you very much, Tracy. I hope everybody can listen to me right now. As Tracy introduced myself, I'm Imran Rizvi, and I'm working as Regional Technical Manager in ABB Canada and responsible for East and Central Canada regions. Today, our webinar is about generator protection fundamentals, and what we expect that as far as the learning objectives are concerned, that by the end of this seminar, you should be able to have a little bit of information about power generation fundamentals, some information about the types of faults in generator protection and abnormal conditions in generators, and then we will talk about typical generator protection as far as this generator protection is concerned. The power station, here in this slide, you can see the diagram of different equipment installed in the power station or a generating station, and as you know, that's the most complex and most expensive part of power system. It consists of both electrical as well as mechanical equipment. Any disruption or interruption in this part of our system, which is power station, has very grave consequences on the power system, both with respect to revenue loss as well as sometimes it is injurious to the human life as well. In this picture, you can see that this whole sequence of power station starts from the turbine, and turbine has got a governor system with it to control the input to the turbine, and then this turbine is connected to the synchronous generator, and synchronous generator is connected to the excitation system over here, and then excitation transformer is here, and we have a generator protection panel provides the generator protection, and we will discuss about it in detail. We have the control systems, then we have the AC-DC auxiliary system, and that system is being fed by the auxiliary transformer. We have a generator breaker over here, and then we have the GSU, generator step-up transformer, for the generating station, and then generating GSU is connected to the high voltage transmission system. So this is the overall structure of a power station shown in this picture. Let's have a look on the typical configuration. It's another way of putting the how these equipment are connected to each other. So if you can see, we will start from the bottom. This is the grounding system of the generator, and then we have the turbine and turbine valve. Then this is the machine, synchronous machine, and then we have the field circuit breaker. We have the excitation system as well as the excitation transformer. Then we have the generator breaker. We have auxiliary transformer, and then we have the main step-up transformer, and then we have the HP breaker, and then we are connected to the bus bar of the substation. So this is the typical configuration of a power plant. As far as the layouts are concerned, we have typically these three layouts seen in our power stations. As you can see, the first one we may or may not have the generator breaker, and the generator sometimes is directly connected to the GSU, and this is the grounding system for this type of layout. And in this layout, we have the auxiliary transformer also connected to supply the power to AC/DC auxiliary systems of the power station. In this layout, we have two parallel generators connected via the generator breakers to the 3-winding transformer, and then to the high voltage circuit breaker, and then the bus bar of the grid. There are several ways to provide generator grounding systems, and we will talk about it a little bit in detail, that what are the benefits and advantages of different types of grounding systems provided in generating stations. The first one is the resistive grounding. So here, a resistance is placed in between the generator neutral point and to the ground. And this resistor is normally in kilo ohms, sometimes 1 kilo ohm, 1.5 kilo ohm, sometimes like this. And this resistive grounding is normally the practice of grounding the generators in our IEC world. Instead of resistive grounding, sometimes we put reactance also instead of resistance, so that's, you call it as a reactive grounding. This one configuration, as you can see over here, is there is no intentional grounding of the neutral point of the generator, and but still there are some capacitances between the stator winding and the ground, which we cannot avoid, and there will be some leakage current, but there is no intentional grounding of the neutral point of the generator. The disadvantage of this type of grounding is that in case of ground faults, there will be high transient over voltages created, and that can sometimes disadvantages to the winding insulations. Another type of grounding is by employing a grounding transformer in the neutral path of the generator. And on the secondary of the grounding transformer is a resistor, and this resistor is normally of the order of 1 ohm. A very small resistance is provided on the secondary side of the grounding transformer. And sometimes you can use the reactance also instead of resistor. And this is the typical North American way of grounding the generators. Another type of grounding scheme could be that to employ the grounding transformer on the terminal of the generator. And the primary side of this grounding transformer is normally Y connected, and the star point is grounded, solidly grounded, whereas the secondary side of the transformer, grounding transformer, is connected to in broken delta formation, and then some resistance is also connected to the secondary winding, and that could be of the order of 1 or 2 or 3 ohm, something like that. So these are the different ways of grounding the generators in vogue in this IEC as well as in ANSI world. Let's have a look on the simplified equivalent circuit of a generator connected with the power system. Right now you can see that here this is the EMF voltage generated in the generator. This is the excitation current. This one is the reactance of the generator, and this one is the reactance of the power system, and this is the voltage of the power system. Now, if the generator is supplying active power to the system, then this machine is acting as a generator. And if it is receiving active power from the system, then this synchronous machine is acting as a motor. If this, on the same side, if this machine is supplying reactive power to the system, then this machine is overexcited mode, or it is in that condition, and it is acting as a capacitor, shunt capacitor, and it is supplying VAR to the system. And if it is receiving VAR from the system, then it is an underexcited machine, and it is acting as a shunt reactor. So these are the different types of, the same machine is acting in different ways in different system conditions. Let's have a look on the generator capability curve. And this curve is quite important when it comes to knowing the performance of the generators, because it tells us several limitations imposed on the performance of the generator in one typical graph. In this PQ plane, we can see that this section AB represents the limits imposed by the field current. So these are the, you cannot increase the field currents beyond this limit. The section BC is the stator current limit, and the section CD imposes the limit for the heating of the stator due to leakage flux. And as you can see over here, that if the active power is being supplied to the power system, then the machine is acting as a generator. But if it is, the direction is reversed for the active power, then the machine is acting as a motor. Similarly, if the machine is supplying reactive power to the system, then it is in the overexcited mode, and if it is receiving the reactive power from the system, then it is in the underexcitation mode. In addition to all these limits, there are certain limits imposed by the turbines as well, and those turbine output limit is represented as BH right here. So this generator capability curve is quite a powerful tool to provide different limitations on the generator performance. This was just an introduction of generator itself. Now let's come back to our topic, that what type of protections or what type of faults as well as abnormal conditions can occur in generators. We differentiate between faults and abnormal conditions because it's not always always important or always necessary to issue the trip command to the generator, because we do not want the generator to be off the power system without any serious trouble. But at the same time, we do not want to damage our generator as well. So it's different to that of the protections provided in the other parts of power systems like transformers or line protection, where we just strip and isolate the faulted part of the power system. So let's talk about the faults what type of what possible faults generators could have. So we can have stator ground faults, we can have rotor ground faults as well, and we can have face-to-face faults in the stator short circuits, and we can have the stator rotor interturn faults as well, and there can be some external faults which can impact the generator as well. So these are the typical faults which can occur in generators. Then there can be several abnormal conditions which can impact generator protection. And those abnormal conditions can be overcurrent and overload conditions. That can be unbalanced load, over temperature, over and under voltage conditions, over and under excitation conditions. Similarly, over and under frequency, over fluxing conditions, asynchronous and running, out of step or pole slip conditions. Generator motoring can also harm the generators and generator systems connected to the generators. Failures in the machine control system, failure in the machine cooling system, and failure in the primary equipment and some open phase conditions as well. So there are several abnormal conditions which we need to take care when it comes to generator protection, and we will touch base to all of these abnormal conditions as well as we go through the seminar. How do we allocate these protection functions in the generating system? Starting from the turbine, we can have the protection of the reverse power. Then we have over frequency and under frequency protection. On the rotor side, we can have the unbalanced protection, loss of excitation protection, pole slipping, ground fault, rotor ground fault protection, and rotor overload conditions. And on the stator side, we can put differential protection, over voltage protection, over fluxing protection, stator overload protection, voltage controlled overcurrent protection, stator ground fault protection, interturn protection, and inadvertent energization of the machine protection. So these different protections can be provided in typical protection schemes to protect the parts of the generating system. As we talked about that generators are the most complex and expensive single element in a power system, so we want maximum dependability and availability of this generating system. Typical generator protection should cover applications for generator as well as generator transformer units, whether they are hydro systems or pump storage, gas turbine, generating stations, combined cycle or steam or cogeneration stations. So the importance of generator protection is extremely high, because of the complexity as well as because of the importance of the generating system in our power system. Let's see the stator short circuits now. Face-to-face short circuits in a generator are relatively rare, but whenever these kind of faults occur, the consequences are quite serious. When the short circuit occurs, the insulation is damaged, and due to the insulation damage, then there are dangers of damaging the winding as well as the stator core. Short circuits in the generator will also cause large fault currents, and these fault currents will result in large forces that will give mechanical stress to other components in the power system. There are definitely risks of explosion as well as fire, because there are lots of inflammable materials in and around the generator, and which can catch fire and give damage to the property as well as to the human life. Also, there can be extremely large forces, mechanical forces and stresses and torsion variations, which can actually destroy the turbine shafts as well as the turbine blades. So we have to protect the face-to-face faults also. How we detect the stator short circuits? There are a number of different kinds of protection capable of detecting and initiating the trip in case of stator short circuits. First of all, the best and the foremost is the differential protection. And differential protection can be generator just for the generator, or for the generator and GSU both in one unit, which is called unit type of differential protection. So, and in addition to differential protection, we can have directional negative sequence overcurrent protection as well, and we can have the impedance protection, we can have phase overcurrent protection, and other type of protections as well, like voltage dependent phase overcurrent and phase overcurrent protection of the block transformer. So there are several ways to detect these short circuits and to eliminate the stator short circuits. Let's talk about now the differential protection itself. Differential protection, as all other differential protections employed, whether it's a transformer, whether it's a line protection, the foremost quality of differential protection is that it is absolutely selective, and the protection zone is defined by the location of the CT. So absolute selectivity can be achieved by the differential protection, and it is very fast as well. There is no intentional time delay for the differential protection, because we do not need to achieve any selectivity or coordination with the other power system elements of protection. The generator differential protection will be able to detect fault currents much smaller than generator current at normal operation, giving a very good sensitivity as well. Current transformers on both sides of the generator winding are normal practice, and while employing this generator differential protection, we must design the current transformer generator protection scheme in such a way to take care of the current transformer saturation in the case of through faults, and it should not give an unwanted trip. So almost the same kind of requirements are there for generator differential protection as we have in any other differential protection scheme. There are four sub-functions of differential protection. The first one is the unstabilized differential protection level. So for the very, very high stator faults, we will use this unstabilized differential protection level, and the protection will give out the trip signal without any regard to the stabilizing quantity. For the stabilized differential protection, this protection can be made more sensitive, where the operation current is dependent on the stabilizing current. The largest measured phase current is taken as the stabilizing current in our ABB philosophy. Negative sequence unrestrained differential protection will discriminate between the internal and external faults, and it is enhanced by the biased differential protection to increase speed and security. Similarly, the negative sequence current standalone fault discriminator gives a very sensitive generator protection, and so the combination of these four actually makes a good differential protection for the generators. As you can see over here, that if the fault is internal, then the neutral side current as well as the terminal side current will flow inward towards the protective object. Then in that case, the I differential would be the vectorical sum of this current as well as the neutral side current. Whereas the bias current would be the maximum of any phase current. In case of the internal faults, the ratio between the differential and bias current would be greater than 1, and that would be an indication of the internal differential fault. In case of external fault, then the direction of the terminal current will be opposite to that of the internal fault, and in that case the I differential will be equal to 0, whereas the I bias would be again the same, that any the maximum of all the phase currents. So in that case, ideally the I differential will be equal to 0 and the ratio will be less than 1. So that would be an indication of an external fault. Let's have a look on the differential protection characteristics. In this characteristics, as we discussed, that this is the unconditional or unrestrained characteristic of the differential protection, and this one is the biased differential protection characteristic with dual slope. The first section of this characteristic covers actually the errors introduced by the differential schemes due to the magnetization current or non-current dependent, non-load dependent part of the differential scheme. So this is covered in this section number 1. From section number 2 is the more current dependent inaccuracies in the differential protection schemes. And the section 3 will be, the slope will be more pronounced and is designed to result in a higher tolerance to substantially take care of the current transformer saturation at high through-fault currents. Section number 3. So this is the typical differential protection characteristics of the differential protection. Generator block or overall protection, including the transformer itself, will also have the same qualities and same characteristics, but instead we will have a transformer now in the zone of protection, so we will have to take care of the delicacies of the transformer also into account. when it comes to transformer differential protection, then we have to take care of the zero sequence current elimination. We have to take care of the vector group compensation and transformer ratio compensation. And then we have to have the unstabilized differential protection as we talked about before. And then we'll have stabilized differential protection. And then, of course, we have to have this harmonic blocking and waveform blocking as well for this switch on to fault features. And then we have the negative sequence unrestrained protection, and then combination with the biased differential. And then we have the negative sequence sensitive differential protection when it comes to the generator unit differential protection. So this was the part where we have covered the the phase-to-phase faults in the stators. And now we will cover the part that how the stator ground fault protection is covered. But before that, yeah, so if you guys have any questions, so please feel free to ask the question in the chat box. We'll be pleased to answer any questions. All right. So let's talk about the stator ground fault protection now. The causes of stator ground fault protection can be numerous, and that could be transient overvoltages, temporary overvoltages, aging of the generators causing the degrading of insulation, high temperatures, mechanical impact, or combination of all. It's quite difficult to pinpoint any single reason for the stator ground faults, but it can be a combination of many reasons. So we normally hear that any single protection cannot cover the 100% stator ground fault. Maximum, it can cover only 95% of it. And this slide actually shows you the reason why the 100% we have to take care of special measures, in fact, to cover 100% stator ground faults. And as you can see from here that only this part of the stator winding is covered by the conventional ground fault protection scheme, and the remaining 5% is not covered. And we'll see different protection schemes which can cover the rest of those 5% as well. But before that, let's see that what are the schemes right now presently in vogue for this 95% stator ground fault protection. We can employ the neutral point voltage transformer to measure the U0, and this will be an indication to have a ground fault protection in the stator. But a disadvantage of this scheme is that that if there is any fault or breakage in this voltage transformer, neutral point voltage transformer, then in that case U0 will be 0, and that will indicate that there is no fault in the stator ground fault, stator winding, and which is not the case. So another scheme which can be used for the 95% stator ground fault protection is that we use a broken delta voltage transformer to measure 3U0 voltage, like here. But in both of these scenes, at the best, what we can do is that to cover 95%, and in certain cases, it can cover only up till 80% of the winding. So the rest of the 20%, or in worst cases it is 20%, but in good cases it would be at least 5% will remain unprotected. So for 100% stator ground fault protection, normally there are two principal methods which are used to protect the 100% ground, 100% stator winding. And these methods are by detecting the third harmonic principle, as well as by the injection method. No matter how good the generator is designed, the sinusoidal waveform generated will never be perfect, and there will be a third harmonic present in the winding in any case. So that harmonic voltage is taken as a criteria to measure the to protect the 100% stator winding. In case of an earth fault or a ground fault close to the neutral, this third harmonic voltage will be reduced and can therefore be an indication that there is a fault, a ground fault in the stator winding. In the other method, we inject a non-harmonic frequency voltage and then measure the corresponding current, and that can also be used as a method for this 100% stator ground fault. The distribution of third harmonic voltages in the stator, they depend upon the generator construction and neutral point grounding system as well. As we discussed before, it will also be impacted by the capacitances, and so there might be several factors impacting the third harmonic voltages present in a generator. So the simplest approach would be that we not only detect an undervoltage condition for the third harmonic voltage, but also we detect an overvoltage condition as well, so to be on the safe side. Here you can see in this diagram, the generator is modeled as part of the winding, where a third harmonic voltage is induced along the winding, represented by the voltage U3. As you can see that U3N is the third harmonic voltage at the neutral point, and U3T is the third harmonic voltage induced on the terminal side. If the fault is close to the neutral point, then U3N will reduce or go to 0 in fact, and U3T will increase. So the both of these criteria is used to detect the ground faults, and this is important for this 100% stator ground faults. The relays, all the modern relays, they follow this this criteria, and there is an algorithm behind it to detect the ground faults without sacrificing any instability conditions. There is another type of protection, impedance protection, which is employed in the generator protection. And this impedance protection has two different tasks. It detects and faults inside the protection zone, as well as it acts as a backup protection for the faults outside the protection zone or outside of the generator as well, and also for the faults on the bus bars. So impedance protection can be used for the generator faults as well as for the faults outside of the generator protection zone. Normally, two zones are employed. Zone 1 covers the generator and transformer, whereas Zone 2 actually covers as a backup of the external faults. Zone 1 will have a very short delay with the task to give backup protection for generator or unit transformer, internal short circuits. And Zone 2 will have a longer delay time and will act as a backup protection for the external faults. As you can see, the coordination of this type of protection with the line protection, we can put for Zone 2 time delay of 0.2 seconds, and for Zone 1 a time delay of 0.2 seconds, and for Zone 2 time delay of 0.5 seconds, because Zone 1 for this distance protection relay is having no intentional delay. So we need to coordinate this distance relay with our generator protection so that to find out selectivity. So let's talk about the loss of field protection. The IEEE 61850 logical node for loss of field protection would be LEXPDIS, and ANSI number is 40 for this loss of field protection. And there are several causes of the loss of field. That can be an open field circuit, it can be a short circuit in the field circuit, accidental tripping of the field breaker, AVR, automatic voltage regulator failure, or loss of field at the main exciter. So there can be different reasons for this loss of field, and the consequences would be quite enormous, and that would be that speeding up of the generator and asynchronous running without the excitation, and some heating will also be there for the end part of the stator. When this loss of field condition occurs, then this slide actually shows the locus of apparent power S, and we can see that the apparent power is reducing, and then it is moving from the generating side to the motoring side, and ultimately it is coming to a point where the generator will fall out of phase and will enter into the asynchronous operation. The loss of field or under excitation protection has an offset MOHO characteristic, and it is essentially has the two zones, Z1 and Z2, and which are combined with the directional element, and it measures the apparent impedances seen out from the generator. And we will have a look on it. As you can see right here, these are the two zones, offset MOHO characteristics, and this is the blinder zone for the restraint area for this under excitation protection. These are the recommended IEEE by IEEE recommended characteristics for the loss of excitation. And we will actually refer to at the end of this slideshow, we will refer to the to different IEEE PSRC working group guides as well as standards, where you can find the details of these characteristics as well as a lot of other information as well. Let's talk about the pole slip or out-of-step protection. This situation happens when machine runs asynchronously with the rest of the system, but with the excitation system intact. And this has got a lot of serious implications when the machine slips a pole or it goes out of step. And there are major mechanical impacts on the turbine as well as on the shaft. How serious these impacts are, right now we will see in this picture, and quite a lot of damage has been occurred in the shaft of the rotor. The pole slip conditions normally occur when there is a sudden rejection of the load, or there is any tripping, inadvertent tripping of the transmission line, and then suddenly some extraordinary load comes on the generator. So either a rejection of load or increase in or sudden increase in the load will cause the pole slipping. What should be the main features of this pole slip or out-of-step protection? Yeah, so it should detect the slip frequencies from 0.2 Hertz to 8 Hertz, and it should alarm before the first slip, and it should discriminate between the generating as well as the motoring direction of the rotor of the phase angle. It should discriminate between the local as well as external power swing centers, and it should trip after a set number of slips, and it should have at that time a set rotor angle to satisfy the trip condition. In this slide, we will talk about the operating characteristics of the pole slip and out-of-step protection. Now, as you can see, that if the generator is faster than the system, then the impedance will move from right the locus of the impedance will move from right to left, and if it is slower, then it will be moving from left to right. An alarm is given out when the rotor angle is more than that of the warning angle. One slip is counted when Z, locus of the Z, crosses between the ZA and ZB line. If it crosses between ZB and ZC, then it is considered as zone 1, and if it crosses between ZC and ZA, then it is considered as zone 2. There are two tripping stages. One tripping stage is that trip 1 will be issued when N1 number of pole slips are counted in the zone 1, provided the rotor angle is less than that of this trip angle. And trip 2 will be issued if N2 counts of slips are recorded in Z2, in zone 2, and rotor angle is less than the trip angle. So these are the two trips. All signals will be reset if the direction of movement is reversed or the rotor angle detects reset without a slip being counted. All these values are also available in the fault record of the typical relay. Let's talk about the motoring protection now. As we discussed that if the machine is supplying active power to the system, then it is acting as a generator. And when it starts receiving the active power from the system, then it acts as a motor. And as far as the machine is concerned, these conditions will not truly impact the machine, but it is very, very dangerous for the turbine. And this picture actually shows you that the erosion and cavitation of the blades of the turbine due to the motoring condition of the generator. And what could be the causes of this kind of condition? It can be loss of the prime mover. It can be in the hydropower plants. It could be the low head of the water level, as well as some load variation can be because of motoring action of the generator. And its effects are that overheating as well as the damages to the turbine blades. The function which is used to detect this kind of protection of this kind of condition is based on the measurement logical node MMXU, and accurate measurements are required to detect this kind of conditions, and multiple choices are available. It can be three-phase, it can be Aron, it can be positive sequence, phase-to-phase or phase-to-ground quantities, and these quantities are used to detect the this directional power protection. Both overpower relay as well as underpower relay are used to detect the power direction criteria, and in combination of both, this protection works. For the overpower protection, as you can see that in case of this type of protection, one should set the relay to trip if the power flow from the network to generator is higher than 1%, depending on the type of the turbine. In the case of low-powered power protection, or one should use this underpower relay, and if the active power from the generator is less than about 2%, then this underpower relay will issue a trip. And as you can see from here that this underpower relay has got a lot of margin over here as compared to the low power, overpower relays. In both these cases, the sequential tripping can be used to mitigate the impacts of the overspeeding before finally tripping the generators. And these are the steps which can be programmed in any modern relay by using the configuration tool. Yet another type of protection is also employed, and that is negative state sequence overcurrent protection, 46. And these negative sequence phase quantities can be calculated by the asymmetrical three-phase currents. Right here, you have the positive sequence quantities and you have the negative sequence quantities, and these are your asymmetric three-phase currents. So the relay calculates the negative sequence quantities, and by using this model, it can calculate the rotor heating limits. Here you can see that this K is the constant depending on the generator design and size. And T is the time in seconds, and I2 is the negative phase sequence current per unit. And this value of the K is provided by the generator manufacturer according to this ANSI C50.13. And this actually K defines or signifies the limit before the damage occurs to the rotor due to negative sequence currents. As far as the causes of negative sequence currents are concerned, there can be an unbalanced load, then transmission circuit can be untransposed. That can cause negative sequence currents flowing into the relay or into the generator, and then there can be an unbalanced system fault, series faults, or some hole could be open or in the circuit breaker, and then there could be an open circuit. So there are several causes to create negative sequence in the generators. These are the IEEE definitions for pole slip, power swing, etc. What is a stable power swing? What is an unstable power swing? And we will refer to these publications as well as these guides at the end of this seminar to get more information about these terminologies. Yet another protection provided in generators is the frequency protection. Over-frequency conditions will occur in the event of sudden rejection of load. Sometimes governor problems can also cause over-frequency conditions. This function can be used for generator shedding as well as remedial action. If the frequency remains above the set value for a settable time, then trip is issued. And this function is normally supervised by an under voltage function. The under frequency conditions prevail as a result of lack of generation in the network. The function can be used for load shedding schemes as well as for the remedial action. And also, this function can be either definite time or a voltage magnitude dependent time delay, which means that the higher the voltage, the longer will be the time. This function is also supervised by an under voltage function and is blocked if the voltage is below the set threshold value. Another type of protection is the over voltage protection. Over voltage protection is provided with inverse or definite time characteristics. Over voltage condition will occur in the power system during the abnormal conditions, such as sudden loss of power or tap changer regulating failures, for example, or open line ends for the line, long lines, for example. So several conditions. Typical settings are 115% with 2-second delay and 130% instantaneous. This function can also be used for open detectors or switch on off of the reactor or capacitors when combined with the directional reactive power function. Another type of protection is the overfluxing protection. Overfluxing causes eddy currents, and eddy currents will cause in turn heating, and that heating can damage the insulation, and it can cause overheating of the non-laminated metal parts, increase in the magnetization current, and increase in core and winding temperatures, and that can cause vibration and noises in the machine. These are the characteristics of the overfluxing protection. This protection is based on the calculation of the volts per hertz ratio. The action of the protection is usually to initiate a reduction of excitation, and if this fails, then a trip is issued after a certain time delay, which can be up to several minutes, in fact. Both IEEE curves as well as tailor-made curves are available, and inverse time as well as definite time trip conditions can be implemented for this overfluxing protection. Thermal overload conditions, that is something which we need to take care of for the generators as well. Before we go further, we will have another question break. If somebody wants to ask, you can ask these questions in the chat box. Okay, so this we were talking about this thermal overload protection. The thermal overload protection estimates the internal heat content of the transformer as well as generator continuously, and then estimates is made according to this thermal model right here. Normally, two levels are available. One level is warning level, and the other one level is the trip level. Another type of protection which is normally applied to the generator protection scheme is the accidental energization protection, and this is, principally speaking, it is a voltage controlled overcurrent function, and this protection is employed if there is a mistake, mistakenly a generator is energized. Yet another type of protection is the breaker failure protection, and it is the it has got the same protection scheme as that of any other breaker failure protection scheme. First of all, the breaker, when the primary breaker doesn't operate due to any fault or any problem, then what happens is that this breaker failure protection comes into an action, and it gives a retrip signal to the same breaker once again. If it doesn't operate, then it gives the tripping signal to the adjoining breakers, and then in certain cases it gives the transfer trip to the remote breaker as well if the adjoining breakers are unable to clear the fault. This is a typical timing sequence for the breaker failure protection. As you can see that this is the instance in which fault occurs. 10 to 30 milliseconds is the protection time, time taken by the relay to issue a trip signal. And from that point, the breaker failure timers T1 and T2 starts. And 40 to 80 milliseconds is the breaker opening time, and then we give a little bit of margin, about 20 milliseconds. And if the current is still there at the end of the timer T1, then a trip signal is given out. A retrip signal is given out. And similarly, after another 40 to 80 milliseconds giving the breaker operating time, and then another margin, then this T2 timer will expire, and if the current is still present, then the adjoining breaker, trip to the adjoining breaker is given out, and that would be the timer T2. This one is the logic diagram of the current-based breaker failure protection, and we have explained it in the previous slide as well. There can be different operating modes for breaker failure protection, and that can be current-dependent breaker failure protection. That can be a contact where you can take care of the breaker failure protection with regard to the auxiliary contact of the breaker, or it can be an AND condition between the current and the contact. So here is the list of IEEE standards and guides. You can go to the website, where IEEE website, and get some more information about generator protection. The IEEE PSRC Working Group J is responsible for generator protection, documentation, guides, and etc., and making any changes to those. So you can refer to those resources as well. ABB has a complete and comprehensive product portfolio when it comes to generator protection. We have REG 650 relays, as well as REG 670 relay, and REG 650 is for small and medium-sized generators, whereas REG 670 can be used for all types of generators. And it has unrivaled selectivity and sensitivity. Lots of communication capabilities are provided in all of our REG type of relays. In fact, it is for all the Rely-On series. We can provide the NP3, I61850, and other communication protocols as well. And it provides innovative tool which simplifies calibration and commissioning. PCM 600 is the only tool which is used to parameterize, to configure, to test and commission the Rely-On series of relays. So there's just one tool, and if you know that tool, it means that you know all the relays. At the end, we thank you for your participation. Shortly, you will receive a link to an archive of this presentation. To view a schedule of remaining webinars in this series, or for more information on ABB protection and control solutions, visit www.abb.com/relyon. At the end, this is a disclaimer. ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be complete presentation for all potential problem solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's website, Protective Relay School, you agree that ABB is providing this information to you on informational basis only, and makes no warranties, representation, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in rely on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. And thank you very much. And with this, we will open the question answer session.
Good afternoon. We have some questions that have come in, and I think we're going to let the line go dead, but I believe Roger is responding to those questions through the question box. So I am going to mute my line and just monitor the question box, but Roger is typing away and responding. So we've had some good questions.
I think we got most. I think we have most of the questions covered right now.
Okay,
so
great.
If anybody has any further questions, just let us know.
Can I? Yes, you can. You all will receive an email after this session with my contact information. This is Tracy, and it will also provide you a link, as Imran said, to the recorded archive. Roger, it does look like a question just came in from Syed.
Yeah, if I had asked if the REG or 650 or 670 are microprocessor-based relays, then you need one for each phase. And the answer is no. There are three-phase relays, and you only need one for a three-phase system. You may use dual relays to get redundancy, but only one is needed for all three phases.
All right, great. I think we're wrapped up. Thank you all for your participation today. We appreciate it, and we hope to see you at the next webinar. Thank you, Imran. Thank you, Rob.